Welcome everyone to this latest installment of our process study webinar series. I'd like to introduce our first speaker, Ruby Leong. Ruby received her Bachelor of Science in Physics and Statistics from the Chinese University in Hong Kong, and her Master and PhD in Atmospheric Sciences from Texas A&M. She's held various positions at the Pacific Northwest National Lab, where she's now a laboratory fellow, and she's also an affiliate scientist at NCAR. Today she'll be presenting on ACAPEX, the ARM Cloud Aerosol Precipitation Experiment. Thanks a lot for presenting, Ruby. I'll turn it over to you.
Okay. All right, thank you. So can everybody hear me well?
Yeah, you sound great.
Okay. Good. All right. Great. First of all, I need to apologize that because I'm at the airport, so once in a while you will hear some airport announcement, but I hope that it goes smoothly. So first of all, thank you for the invitation to give a presentation to the committee or the working group. So I'm going to talk about this ARM Cloud Aerosol Precipitation Experiment, and we call it ACAPEX. And I listed the organizing committee over there. So we have a number of people involved. As a matter of fact, I think just maybe like 2 or 3 months ago, you guys already heard about cow water experiment from Marty. So ACAPEX is part of cow water and is specifically funded by Department of Energy. So since Marty already gave some introduction to cow water, so I'm mostly today going to focus on the ACAPEX aspect of the field campaign. Okay, so since the field campaign is funded by Department of Energy through the ARM program, just want to give you a little bit information about the ARM program, just in case some of you may not be familiar. So the ARM Climate Research Facility essentially is an observation user facility, meaning that basically anyone can propose to DOE if they wanted to use the facilities, which include like permanent sites as well as mobile facilities and aircraft. So anyone can actually write a proposal to DOE if they wanted to use these facilities to do climate research. And so the main mission for ARM is essentially to strategically locate these in situ as well as remote sensing observatories, and they are designed to improve understanding and representation in Earth system model. So the modeling aspect is a very important component for ARM program because our ultimate goal is really to improve modeling by collecting observation data that can give us insights about the processes as well as use the data to evaluate models, etc. So this is an aspect that I would like to particularly highlight. So in terms of ACAPEX, essentially we ask several questions. At the very high level, our main question is really about how much water or how much precipitation is produced when an atmospheric river makes landfall in California. We know that by now atmospheric rivers actually happen quite a few times a year, making landfall in California or along the west coast of the United States. And so because of some of the features of the atmospheric rivers, including the strong wind speed, and it carries a lot of moisture that's usually coming from the tropics, and the atmospheric stability is usually kind of neutral. And because of these 3 factors, atmospheric rivers are really important ingredients for producing heavy precipitation in western United States. But the main question that we ask is also like, well, do the models get it right or not? For NOAA, the main interest is really about short-term forecasting. But for Department of Energy, we are also very much interested in how well climate model captures atmospheric rivers as well as the uncertainty in projecting the changes in atmospheric rivers in the future. So here I show an example of a model that we actually have been using in the last 2 or 3 years. It's a global variable resolution climate model. So we can select a domain where we have high resolution over the Pacific Ocean and the western United States to really better capture the narrow filamentary structure for the atmospheric river. And we do run these simulations on high-performance computers in a climate simulation mode, but we can also run these models in weather forecast mode. So during the ACAPEX field campaign, we actually have run these type of models in a forecast mode to determine how well the model captures the moisture fluxes, etc. So besides the total amount of precipitation, we also really keen in understanding the phase of the precipitation, because in California, whether the precipitation comes in as rainfall or snowfall makes a big difference. Usually when you have this snowfall in the mountain, and so the snow is really collected on the ground, a snowpack, and then during the summertime or early spring, then the warm season comes, and then the snow melts and it refills the reservoir. So really able to determine the phase of the precipitation is also an important part of this field campaign. So one factor that we have learned over the years, at least in the last 4 or 5 years, is that the phase of the precipitation seems to actually influence a lot by not just the temperature of the storm itself, but also affected by these aerosols that are coming in from the Pacific Ocean. And by now we know that some of these aerosols can actually be carried a long way from, let's say, the African desert or the Asian desert, and carry a long way with the atmospheric river. And these aerosols actually have a large impact on the precipitation in terms of both the amount as well as whether the precipitation comes in more as rain versus snow. So an interesting figure over here that I show is based on a model simulation. So if I don't tell you what it is, you might think that it looks like an atmospheric river, right? Because usually we see this kind of structure coming in from kind of near Hawaii and then making landfall in the west coast. But in this case, this is actually showing the amount of dust simulated by our model. And you can see tracing back, a lot of the dust actually comes from the desert area in Asia as well as in Africa. So I will talk about this more in a minute. So as I mentioned, ACAPEX is not an independent field campaign. It's part of a larger field campaign together with NOAA and several other agencies. So it happened between January and March of 2015, last year. And we all know that last year was a pretty dry winter. This year seems to be better because of the El Nino situation. But last year it was quite a dry year. Despite that, we were still able to sample quite a lot of atmospheric rivers, although not many of them made landfall in the western United States. But in any case, so the main objective is really to improve understanding as well as modeling of the role of atmospheric rivers together with the aerosols that usually kind of hitch a ride together, and then they affect the precipitation in California. So the participating agencies, there are several. So NOAA is definitely a major player, and they provided the ship Ron Brown as well as 2 aircraft, the NOAA G4 and also the NOAA P3. DOE is responsible for the ACAPEX part of this field campaign, and DOE provided an aircraft G1 as well as mobile facilities, the armed mobile facilities, which we put on Ron Brown. And then NASA, towards kind of like in 2014, they decided to join the field campaign, and so they have aircraft YAO-2, which is a nice opportunity to really look at cloud and aerosols together with the G1 aircraft. And at the same time, the Naval Research Lab provided these AXPT that can be dropped by the NOAA P3 so that they can make measurements in the ocean. And then there's also a land-based laboratory, which is funded by NSF, mostly through UCSD as well as Colorado State University. So they have been making measurements in this area is called Bodega Bay. It's in the coastal area where atmospheric rivers oftentimes also make landfall. So these measurements they have include like cloud and aerosols, etc. So again, let's go back to the key science questions. There are three different components that I would say. So the first one is really related to atmospheric rivers. So we wanted to be able to quantify how much water vapor is transported by atmospheric rivers, because it's important, particularly for the weather forecast problem. We know that the water vapor content is a big factor in controlling the amount of precipitation. So we wanted to know the vertical distribution of the water vapor, as well as the sources of water vapor, because the traditional understanding is that a lot of these water vapor carried by the atmospheric rivers are coming from the tropical area. But we don't really know whether some of the water vapor or how much of the water vapor actually may be coming from evaporation at the ocean surface, which could then be carried along and then trained into the atmospheric river and make landfall. So both the sources and the amount of water vapor is what we wanted to get at, as well as the cloud microphysical processes that affect precipitation at landfall. And then the second major component is to understand the aerosol cloud precipitation interactions. As I briefly mentioned before, aerosols such as dust carried along with the atmospheric river can have a large impact on the precipitation. So we wanted to know the distribution, the characteristics, as well as the sources of aerosols affecting winter precipitation in California. And then we also wanted to know how aerosols influence precipitation, not just where they come from and what they are, but also how they interact with the cloud and therefore affect precipitation in different kinds of storm environments. And then the third one is really an interaction between the first two objectives, essentially looking at interaction between atmospheric river and aerosols. So here we wanted to know whether aerosols coming along may actually influence the evolution and the structure of atmospheric rivers, because having aerosols in the environment, they can produce heating and they can also affect cloud formation, which then could also affect the diabatic heating. So together they might play a role in terms of the evolution of the atmospheric river over the ocean, as well as after atmospheric rivers make landfall. And so for all of the above, we are very interested in how well the models capture these kind of phenomena, using the data to help us evaluate the model, as well as provide us with better mechanism to represent in the model. So now focusing a bit more on the field campaign, the ACAPEX side of it. So there are many different observing platforms, but from the DOE side, as I mentioned, there are mainly two. The first one is the Armed Aerial Facility, which is essentially the Gulfstream 1 aircraft. And then the second one is the Mobile Arm Facility, which is put on top of NOAA 1 Brown. And so here is a picture showing the different types of instruments that we have as a package in the Arm Mobile Facility. And so now I can go through the instruments a little bit, but not to a lot of detail, just to tell you the different categories of measurements that we can make with these instruments. So with the Arm Mobile Facilities, which are put on 1 Brown, we essentially have several types of instrument measurements that we can make. The first one is an instrument set which is called the Aerosol Observing System. So it has the ability to do in situ measurement of aerosols in terms of the size distribution, etc. And then we also have cloud measurement, and these are all based on remote sensing technique. So we have vertically pointing W-band cloud radar. We also have zenith pointing radar, microwave radiometer that measure water vapor, etc., as well as the cloud base. So all of these can provide us information about the clouds together with the atmospheric river. And then it can also make meteorological measurements in terms of wind profiler, atmospheric sounding. We release radiosonde very often when we were in an atmospheric river condition. We also have a portable radiation measurement package, and so this allows us to also look at the solar radiation as well as the radiation impacted by aerosols. And then another important set of measurements that we want is really the aerodynamic fluxes. So this can contribute towards understanding the moisture sources how much of the moisture might be coming from surface evaporation in the ocean. Turns out that actually this is an interesting thing because under an atmospheric river, you might imagine, because the winds are typically pretty strong at low level, so you might imagine a lot of these evaporation going on. But another factor to consider is also that the atmospheric rivers are actually really warm. So compared to the ocean sea surface temperature, so you have potentially a much warmer air above the sea surface, and therefore it's really unclear whether the strong winds play a bigger factor or the wind or the temperature gradient play a more important factor in terms of determining the surface fluxes over the ocean. So, besides the armed mobile facility, we also have the G1 aircraft. So the payload itself contains about 40 different types of instruments. It's not a very big aircraft, but we do pack it tight with a lot of different types of instruments. So particularly of interest are in situ measurements. So we fly through clouds. We have in situ measurement of different cloud properties like liquid water, total water, ice water content, as well as the size distribution of these cloud ice as well as cloud water. And then we also have aerosol measurements. We have total concentration, size distribution, optical properties, physical chemical composition, so we know what type of aerosols they are and whether they are absorbing or not because of the optical property. We can also tell whether they are serving as cloud condensation nuclei that nucleate cloud droplet, or they are serving as ice nuclei that are more like creating or nucleating ice or crystals. Right? So this is really important for us to understand the cloud microphysical processes that are going on in the atmospheric river. And then we also have these trace gases measurement. So during the Cloudwater 2000, so generally we kind of combine these Cloudwater 2 and ACAPEX field campaign. We just called it the Cloudwater 2015 field campaign because the campaign itself does involve several different agencies. And so here we look at the timeline. So the campaign started around mid-January of last year, 2015. But actually for the ARM program to join this field campaign, I put together the proposal back in 2012. That was almost like 3 years ago, 3 years before the field campaign. So the proposal was submitted in April of 2012, and after peer review, it was approved in October of 2012. So we had quite a bit of time in between to really plan for the field campaign and also get other agencies get on board in terms of what type of instruments and platforms they can contribute. So as I said, the campaign started around mid-January. So we have the NOAA 1 Brown carrying its own instruments as well as the ARM mobile facility. So this ended around kind of like early February timeframe, and so it arrived in San Francisco, and then later on went to the port of San Diego, and then we moved the instruments over there. So the DOE G1 aircraft also started in mid-January, and it lasted until the end of the first week of March. And then the NOAA G4, this is a really important platform for us because it has the ability to fly really longer distance, and it can provide fuel for like many hours. So oftentimes when we had atmospheric rivers that did not make landfall in California, so G4 is the aircraft that we can use to fly out to the ocean and actually still do the measurements for the drug zones to measure the moisture content, vertical profile of moisture content. And then another aircraft is NOAA P3, so it has radar as well as some cloud probes to measure cloud microphysics as well. And then the NASA ER2 flying very high, and it has a lot of remote sensing instruments to measure cloud microphysics as well as aerosols. And then there are a lot of different ground-based instruments that have been instrumenting in that area over the last few years, and they remain there. So part of it, the important part is the NOAA hydrometeorological testbed, and then also the NSF-funded part in Bodega Bay where they make measurements of aerosols and clouds. So here we use the notation C to indicate some of the coordinated platform activities, So during the field campaign, sometimes the aircraft were able to make coordinated flights so that we can contribute a larger data sets of different types of instruments for the same event or the same phenomena. And sometimes the aircraft also coordinated with one ground, so we fly over one ground so that we can have upward-looking remote sensing instruments from AMF together with downward-looking radar from the aircraft or in situ measurement from G1. So we have actually quite a lot of these different coordinated flights and coordinating with the ship. So here, just give you a little bit more detail in terms of the ACAPEX platform activities. So the G1 aircraft in that kind of like a little less than 2 months period, it flew a total of 28 different flights. So 8 of the flights flew through atmospheric river condition, and then 6 of the flights in coastal stratus and stratocumulus condition, and then 4 flights in frontal or Brother Klaus, and then 10 flights were mainly used fly in clear sky conditions, so mostly characterizing the aerosols and environment in that area and where the CCN are coming from, etc. And so of the 28 flights, 6 were coordinated with the NASA YAO-2, and then among the 6 coordinated flights with YAO-2, 2 of them were also coordinated together with NOAA G4 and the P3. Okay, so as I mentioned, so during the field campaign, there weren't a lot of atmospheric rivers that were able to make landfall because last winter there was a big high pressure system basically sitting in the California coast, in the Pacific Ocean. So a lot of atmospheric rivers were really directed either to the north or didn't make landfall at all. But we did have a few atmospheric rivers that made landfall, and one of which was a really pretty big atmospheric river, and it occurred between February 5th to February 8th. So in the next few slides, I'm just going to give you a little bit more information about what we measured during this particular atmospheric river event. So on February 5th, the atmospheric river was still in the ocean. It hadn't made landfall yet. So the agencies together planned a joint experiment where we used all 4 aircraft, so 2 of them from the NOAA aircraft and then the DOE as well as the NASA aircraft, jointly together fly out to the coastal area. This is not too far, but kind of like pushing the limit for the DOE G1 aircraft because we can only fly about 5 hours at most with the fuel that we can carry. But we were able to join this part, and we flew out to the ocean and flew back. So we had measurement from 4 different aircraft together with there was actually an overpass by the Terra satellite, and so there was a pretty interesting data set. But this is a photo that I took. I was on the G1 aircraft, so we reached down to pretty low above the sea, and we can actually see the Ron Brown kind of tossing by the strong winds in the atmospheric river. So I took a picture of that. So here is the YAO-8 data set of the integrated water vapor, and you can see most of the water vapor are concentrated close to the surface. So here I look at 3, the instrument that we have from G1 and P3 together with the ship. So this is the same event that I just talked about on February 5th. So G1 flew out and then flew back, and then P3 flew out and then make kind of like a zigzag and then went back, came back, and then so the circle area is where the Ron Brown was. So then we have different types of instruments that allow us to look at the clouds. For example, here we show the cloud probe data showing the cloud drop size, and we can see that this is the in situ measurement coming from G1, and this is the in situ measurement coming from P3. Each has different cloud probes to look at cloud drops of different sizes. So we see that mostly the cloud drops are relatively low concentration, and the size are pretty small, roughly kind of like around the 10 micron to 20 micron kind of size. And looking up from the AMF on Ron Brown, using the radar, we can tell the freezing level. As you can see, the big difference between the warm rain and then up above is the cold cloud. And so this is showing the temperature profile as well as the height where G1 flew. So we are now using this particular set of measurements from different platforms together to look at cloud microphysical processes. And then in the next few slides, I'm going to talk to you about several different flights that G1 made between February 6 and February 8. So on February 6, the atmospheric river made landfall, and so we made a flight in the mountainous area. So we do this kind of lawnmower pattern. So along the valley kind of direction, as well as up the hill slope kind of direction, going all the way to pretty high elevation. This is where Lake Tahoe and a lot of precipitation and convective clouds over there. And then February 7th was after the atmospheric river made landfall, and we were in a post-frontal condition, so the clouds were much colder. And then on the 8th, the atmospheric river continued to produce a lot of precipitation after making landfall. And there was a Sierra barrier jet along the valley, the Central Valley, and so we made a flight along the valley to really measure these Sierra barrier jet, and then come back, we do this lawnmower pattern again. So it's really good for us to be able to look at the atmospheric rivers. For that particular atmospheric river event, we looked at it before making landfall, during landfall, as well as after landfall in the post-frontal condition. And then we made the same kind of flight in the same environment. So that allows us to really see whether there are major differences in terms of the aerosols that might be affecting the cloud and precipitation during the different parts of the different life cycle, part of the life cycle for the atmospheric river. So here are just some pictures that I took when I was on the G1 aircraft. So now let's take a look at the February 6th. So February 6th, these are the orographic clouds. So we flew a little bit over the Central Valley, but then most of the time we spent was over in the Sierra Nevada mountain. And so you can see images of these clouds when we flew through the clouds. So the temperature was relatively cold in the mountains, so we see a lot of glaciation, a lot of cloud, ice crystals and things like that. But at the same time, we also often see supercooled cloud drops that are really, really tiny. Here, the supercooled cloud drop occur at roughly about minus 10 degrees Celsius. It's not like too cold, but later I'm going to show you that sometimes in situations with much colder temperature, we were still able to see supercooled cloud drops. So here, on the same day, February 6th, so we did a back trajectory analysis to determine where the air that produced the cloud in the mountainous area come from, and mostly we found that they kind of come from the Pacific Ocean because they do come with the atmospheric river. So, and they are relatively clean with a very low concentration of cloud condensation nuclei, which we call CCN. And then on February 7th, this is now the post-frontal environment because the atmospheric river already passed through. Temperature was much colder. CCN concentration remained really low. And when we look at the cloud drop size, we can see that the cloud drop size are still relatively small. And we also look at the particular environment when we flew over to the Sierra Nevada. The temperature was really cold because this is post-frontal environment, and we reached a temperature of minus 38 degrees Celsius over here. And I'm going to show you what kind of cloud images we see next. So here we can see the cloud images of, So we can see let me try to go back. Okay, so here we can see the cloud images during different part of the flight. So when we were going uphill in the foothill area, we see a lot of these ice crystals. They were formed mostly by turbulence in the convective cloud. But then as we reach a kind of like the ridge of the mountain at about minus 38 degrees, we actually see a lot of very tiny supercooled cloud drops which makes us wonder, like, why would we be seeing these supercooled cloud drops if the environment is so clean? So supposedly, if you are in a very clean environment, you expect that the cloud drops to be very big, and big cloud drops would glaciate very quickly, and you wouldn't expect to see this type of tiny little cloud drop that we see in this figure, for example. So then we started analyzing the type of aerosols that we see in that environment. And interestingly, even though the environment itself is pretty clean, meaning that the concentration for CCN and IN are very low, but the chemical composition is quite interesting, because oftentimes we see these either like black carbon or elemental carbon or organic carbon, etc. And we can not only one instrument show that these are the kind of aerosols that we get, but if we look at the light absorption coefficient, we can see that these aerosols are actually highly absorbing, which is consistent with the type of aerosols that the instrument said that they were. These are like black carbon and things like that. So, but in an atmospheric river type of environment, you might think that the air is mostly coming from the ocean. It should be relatively clean. But when we did a back trajectory analysis, we actually determined that the air that is behind the atmospheric river in the postfrontal environment actually arrived from East Asia, which kind of explains the content of the type of chemical composition in the aerosols that we are seeing. And on February 8th, again, we flew over to the mountain, and this day there was a Sierra barrier jet, so we flew along the valley, and then coming back, we flew along the mountain ridge, and we see a lot of ice crystals that were formed, and these were like mostly formed when we have like convective clouds above us, and so some of these are formed because of the secondary ice nucleation process. But then at the same time, we again also see some of these like supercooled cloud drops at a very low cloud temperature. So again, doing the analysis for the different types of aerosols, we see that they are either like dust. So this one here is particularly indicating dust. And we also have these organic carbon, which are mostly probably coming from polluted environment. So again, doing a back trajectory analysis, we determined that a lot of these are really coming from East Asia. So there are some salt on top of dust, as well as these organic carbon. So then we identified that it's really important for us to understand the relative impact of CCN and ice nuclei on the supercooled liquid and the cloud phase, because we do have an environment where we see both supercooled cloud drop as well as ice crystals. So we did some model simulations, essentially did a lot of different sensitivity runs to determine how sensitive supercooled liquid water is to the concentration of cloud condensation nuclei and the concentration of ice nuclei. So I just want to go through this a little bit because I think this is a pretty interesting result. So these dashed lines are for different concentration of CCN. So if we look at over here, the x-axis, we show the liquid mass fraction, and then the vertical axis show the temperature of the cloud. And you can see that in a mixed phase cloud, as we increase the concentration of CCN, you can increase the liquid mass fraction, because then now you have like smaller cloud drops and they can actually increase the total amount of water content of the cloud. But at the same time, when you increase the concentration of CCN, it moves the temperature of the cloud to colder temperature. So now you can have supercooled cloud drop at even lower temperature, meaning that it actually expands the mixed phase zone of the cloud. And the other way around, when you look at the concentration of ice nuclei, if you change from a low concentration to a high concentration, you immediately significantly reduce the amount of liquid water, because now even just adding a little bit of ice nuclei, the cloud can glaciate, and it immediately removes a large amount of liquid water and to form the ice crystal. And at the same time, when you increase the ion concentration, you will change the temperature of the cloud so that the cloud drops now cannot really form at very low temperature. So the temperature that you will find cloud water becomes like warmer, and so essentially narrow down the mixed phase zone if you increase the concentration of ice nuclei. And comparing two different types of cloud, cold mixed phase orographic cloud versus warm mixed phase orographic clouds, we see that the range of different amount of liquid water fraction depending on the ice nuclei concentration is a lot more sensitive in cold mixed phase cloud compared to warm mixed phase cloud. And following the experiment, we also did some model simulation of dust. We really wanted to know, like, climatologically, how often do dust really come to the western United States from Asia or from the desert of Africa. So we did some simulation and looking at different months of the year. We do find very different sources of dust reaching California coast. Here, the red means dust that are locally generated in North America. Usually they come from kind of like the Sonora Desert, kind of southern area. And we also have dust that are coming from East Asia, dust coming from Africa, etc. So you can see that in the early season of a year, usually sometimes you have these episodic dust that are coming to California from the Sonoran Desert. But you can also see a very significant amount of dust in the early winter season coming from North Africa. And then in the springtime, part of it also comes from East Asia. So we continue with this type of analysis with model and then using the observation data to really learn about the data sets and the long-range transport of dust. So here a very brief summary. So we have a lot of information about this field campaign. So these are the links to the field campaign as well as the feature story. During the field campaign, we actually got a lot of coverage by media. A large number of that, we capture that in this website. And so ACAPEX is part of Cloudwater, and so the Cloudwater 2015 field campaign also had several websites with information that we can actually go back and look at all these weather forecasts during the field campaigns to help us understand the large-scale environment, etc. So the ARM data repository is located over here. And so ARM's policy is that 6 months after the field campaign, we have to post all the data after all the QC, QA, and things like that. And so the data sets from ACAPEX have been on this repository since last September or October, 6 months after the field campaign. And so last winter at the AGU 2015 in San Francisco, we had 2 sessions, an oral session and a poster session with a lot of different talks and posters related to this particular field campaign. Scientists have been starting to analyze the data, use the data to evaluate models, etc. So a very brief summary again about the particular atmospheric river event that we measured. We found that during the atmospheric river, the atmospheric environment is usually very clean, meaning that the concentration for aerosols are typically low because there's a lot of precipitation that really removes the aerosols from the atmosphere. But even though the concentration of aerosols are low, we find that those aerosols could be coming from Asia, and they could be really related to like organic black carbon, etc., which really change the property of the cloud because they are hygroscopic. So then cloud drops, they don't really like to form a lot in that kind of environment. So usually they are really small, and they can remain supercooled cloud drop at very low temperature. So this is part of these phenomena that we found that we would continue like to be able to perform modeling experiment to really better understand this kind of environment and the impacts of aerosols on the cloud and the precipitation. So that's all I have.
According to